is to fill out my teaching evaluations if you haven't done so already. So we're up to 20 of you guys. We're making progress. I'm going to keep this tally until we get all 52. So, if you want to stop seeing this slide before the end of the semester, then everybody go home and fill it out, and then we can skip this part of the class, okay? All right, so we're going to continue working on stuff that we've talked about. Now, here's something that has been on my mind lately about sort of how do I think about antiderivatives and derivatives. And I realized that when I'm looking at a function, the first thing I take note of is its structure, right? I look at it and I say, is this a sum of two functions? Is this a product of two functions? Is this a quotient of two functions, right? And that made it really easy when we were taking derivatives to figure out which derivative rule to apply, right? Well, the same logic goes into finding antiderivatives. So if you're still sort of struggling with the sort of computational aspect of finding antiderivatives, my suggestion to you is to really think about the structure of the function that you're looking at inside of the integral, okay? Because remember, finding antiderivatives is really just sort of doing derivatives in reverse, right? So, for example, when I look at the constant multiple rule for a derivative, if I were to think about that in terms of antiderivatives, well, then I could, if I had something that looked like this, right, inside of my integral, where I have some constant multiple of a function, little f, then in the same way that you sort of leave the constant multiple alone and then multiply by the derivative of the function, you can think of this as it doesn't change. That process doesn't change, right? You still have the constant multiple times the integral of your function, okay? So you can pull this constant out just the way we do when we take a derivative, okay? So here's all of the rules. Oh, no, don't do that. Hopefully it doesn't turn the page on me. Oh, why does it do that? Oh, no. Okay, so we'll stop one short. Okay, so what's the one that's missing? Product rule, right? We've got everything else up here. So in the same way, if you have an integral where you've got the sum of two functions on the inside, so something like the integral of 3x squared plus 2x dx, right? Then I can find the antiderivative of this by finding the antiderivative of the pieces separately, right? Now, the more complicated derivatives, should I finish this? What's the answer? What's the antiderivative of 3x squared? X cubed. What's an antiderivative of 2x? What's missing? Let's see. Okay. So now, so the reason why I had all of the rules up here, and don't know why that my computer hates me, was because I wanted to emphasize that when you have the product rule, when you look at the sort of the outcome of the product rule, right, the outcome is not a product, right? It's a sum of two products. So the only time I should sort of be thinking of the product rule in reverse, if you will, is if I actually have the sum of products, right? So like, let's build one together. So Joseph, what's your favorite function? Not too complicated. Favorite function? Sine of x. Okay. Rashay, what's your favorite function?
My favorite function is
Oh, that's a rule. I just want a function.
Oh, favorite function.
Your favorite function.
X squared.
Okay. So sine of x times x squared. Okay, so what's the derivative of this? Huh? Cosine x times x squared plus, oh, okay. Well, I'm going to write the sine of x first, and then times 2x, right? Okay, so that means that the integral of cosine x times x squared plus sine of x times 2x dx is equal to what? Sine of x times x squared. What's missing? Plus c. Okay? Yes. What just happened? Oh my gosh. Right, okay. So what I just did was I started with a function, sine of x times x squared. I took its derivative, right? And I got this thing over here. And then I said, well, if I take a function and find its derivative, then I could reverse the process and find the antiderivative of this thing, right? So I took the integral of that function, and so when I do that, I'm looking for the antiderivative of this inner function. Well, an antiderivative of this inner function better be the thing that we took the derivative of in the first place, right? Because we're reversing the process. So the original function pops back out. So when you think of differentiation and finding antiderivatives, this is a reversal of the process, right? You could just sort of cyclically go around in a circle if you wanted to. You start with a function, you find its derivative, and then the antiderivative better get you back to where you started with, right? It's sort of like the idea of an inverse function, but instead of an inverse function, it's like an inverse process, if you will, right? So that's what we're doing here, right? And so this is what I've been talking about when I say, all right, you think you found an antiderivative? How would you check it? You take the derivative and see if you end up with the thing that you started with, right? So this is exactly what I mean when I say that, okay? Mind-blowing? Not too bad? A little bit cool? Okay, let's, you want to do one more then? Just to see for reals what I'm talking about? So let's do one with a quotient, okay? So let's say, Taylor, what's your favorite function? Okay, natural log of x. And, e to the x. Okay, let's take the derivative of this bad boy. Okay, so help me out. What do I write? E to the x. Right? Am I done? Nope. Over? Yeah, e to the x squared, or e to the 2x, okay? So what have we just done? We've taken a function and we found its derivative. In terms of meanings, right, if this had been some accumulation function, we found its corresponding rate of change function, right? So now if we were to pretend that we didn't know this thing in the first place, right, the accumulation function in the first place, and we said, oh, all we have is this rate of change function, okay? But we wanted the accumulation function. Well, you find accumulation function from rate of change through this process, right, of integration. So here's my rate of change function, and I want the corresponding accumulation function, right? Well, in terms of the things that we've discussed, that means we're looking for an antiderivative of this rate of change function. That means we're looking for a function who has this thing as its derivative. We just did that, right? So a function that has this crazy looking mess as its derivative is natural log of x over e to the x plus c. Okay, yeah.
So like for that, what if you were given a reduced form and you had to find an antiderivative? So then, or would you always give this to some like a form that would be like, oh, okay, that's a definitely, you can just look at it and follow it. Because like what if you couldn't you reduce that?
This is absolutely reducible, yes. Now, the question that you're asking sort of doesn't apply because my goal here is not to trick you and not to scare you, okay? I'm showing you this because I want you to understand the process of how, like, one process sort of undoes the other, okay? But I'm not going to give you something that looks like this on the test. Not this complicated, right? Okay. Now, something that would be fair game for the test is something using this rule, okay? So the chain rule is a rule that spits out something of the form of a product, right? So when I see a product inside an integral, my gut instinct is to think, maybe this came from a composition of functions, right? Because things that have derivatives that look like products were composition of functions to start with, okay? So this is what I mean when I say think about the structure of what you're looking at, okay? So let's look at an example of the chain rule, okay? So remember, this is what the chain rule says. If you have a composition of functions, then the derivative is the derivative of the outer with the inner plugged in times the derivative of the inner function, okay? Now, here is an actual example of a composition of functions. So what's the inner function in this composition? Sine of x, and what did we plug it into? E to the x, okay? Now, so that means if I take the derivative of h of x, what am I going to get? Does everybody have an answer in their brain? Ahmed, you got an answer in your brain? That was a no? No, I'm talking to Ahmed. Don't know? Can we help him out? Do you have an answer in your head? Gotcha? Yeah. E to the sine x times cosine x. I like it. Okay? So, all right. So if we're keeping in mind this reversal idea, instead of talking about h of x as the original function and h prime of x as its rate of change function, what could I instead talk about? If I start with e to the sine x cosine x, and imagine that as sort of my starting position, then what is e to the sine x in relation to e to the sine x cosine x? So this function is the derivative of e to the sine x. What would I call the top function? Okay, so if I'm thinking of h prime as a rate of change function, then I could be thinking of h as an accumulation function. Okay, but what if I'm thinking more abstractly, right? So I use this word derivative. What would be the corresponding word to describe this thing? The antiderivative. Of what? Of itself? Is this correct? No. What's missing? Cosine x, right? So this is the relationship, right? So this thing is the derivative of that thing, And this thing is the antiderivative of this thing, right? A reversal of processes, okay? So when you hone in on the structure, right, you've got a product of two things where you can see a composition in the first piece and the corresponding correct derivative in the second piece. So that means if you were to look at the antiderivative, right, you would end up back where we started. So switching the order of your perspective. Okay. Now, here's the thing. If you can eyeball that, that's fantastic, right? Some people struggle to eyeball it though, okay? So there is a technique that is talked about in your textbook, I think, that's called substitution, okay? And so the method that I'm about to show you is simply a formalization of eyeballing, okay? That's all it is. So if you are really comfortable doing the eyeballing thing, go for it, okay? Don't feel restricted to what I'm about to show you. But if you sort of look at this and you're like, I have no idea what I'm looking at, okay, then here's a technique that you can use. So it's called U substitution because we almost always use a U. And the idea is that you look for something kind of complicated in your integral, inside your integral, and see if you make that thing U, would its derivative sort of fill in the rest of the integral for you? Okay, so what do I mean by that? If I let U equal e to the sine x, so right now I'm trying to compute this integral. Okay. When I look at this integral, the most complicated looking piece of it is this chunk. Do you agree? So I'm going to let U equal that chunk and see what happens. Okay. So if I were to take the derivative of U, then this is the derivative of U with respect to x, right? So far, so good? Okay. Well, all this means is that for little changes in x, the corresponding changes in U are like this, right? So I can rearrange that and say little changes in U correspond to this rate times little changes in x. So I'm reinterpreting, or I'm using our meaning for rate of change here, right? So this is giving me the rate of change of U, can be computed using this formula, right? I'm using our interpretation of that to rearrange, not really rearrange, but rewrite little changes in U are the rate times little changes in x. Now notice that this precisely gives me the thing that I started with in my entire integral, right? So I could rewrite this integral as the integral of du. Do you see it? Okay. So then now my variable that I'm sort of taking an antiderivative with respect to is u. The thing inside the integral is really just a 1. So what's an antiderivative of 1? So I hear some people saying x, but remember we're using the variable u. So it's just going to be u plus a constant, right? But remember, u was e to the sine x. Okay? This is one way to do u substitution for this specific integral. There's actually more than one way that works. So let me show you another way. Instead of using a u, I'll use a v because I'm going to keep this up on the screen. So let me say let v just equal sine of x. Okay. Then what's the derivative of v with respect to x? Cosine x, right? And so if I interpret this meaning, this means that little changes in v are computed by doing the rate times little changes in x. Do you see it? That's the meaning that we've developed for rate of change, okay? And then if I sort of go back to my original integral and rewrite it in terms of v, well, I've got e to the v, because v is sine of x, and then cosine x dx, hey, that's right here. So I've got e to the v dv. So what's an antiderivative of e to the v? E to the v plus c, right? Because the derivative of e to the v with respect to v is e to the v. Okay, but I started this problem in terms of x, so I should end it in terms of x. So let me replace the v with what I started with, which was sine of x. So e to the sine x plus c. Okay, so that's another way to use, quote, u substitution to solve this. Okay, and so the first way that we did it with the u was to pick the most complicated looking piece inside the integral, right? So we used the e to the sine x. The second way that I did it using the v was to pick a function in, like, an inner function of a composition. So I saw e to the sine x. I said, that sine x is the inner function inside a composition of e to the x and sine of x. So I'm going to choose that thing to be my v and see if it works out nicely for me to be able to so the goal of this substitution process is to be able to rewrite an equivalent integral that's just simpler, right? So instead of starting with an integral of e to the sine x cosine x, look at what we got. We got an integral of 1. Well, that's just about as darn easy as it gets, right? Or an integral of e to the v. As far as functions go, that's pretty nice, right? So this process of u substitution is meant to simplify what you're looking at inside your integral, okay? So that's why I look for the complicated looking thing and replace it with something simple, like u, okay? Okay, so this is the method. It's called u substitution. If that confuses you, eyeball it, okay? And keep eyeballing it until you find a function whose derivative gives you the thing that you started with. Yeah? It's the rules for derivatives, only in reverse, right? Do you see it? Let me, because this, I was waiting for that question, right? So, rules for antiderivatives. Cheat sheet. The antiderivative of 0 is c. An antiderivative of n x to the n minus 1 is x to the n, right? Antiderivative of e to the x is e to the x. Antiderivative of 1 over x is not natural log of x, but natural log of absolute value of x. Okay, so that's the one where I catch you, right? Okay, all of the trig functions in reverse, right? So if you wanted to make something clean and pretty because you love to memorize lots of things, what would you do? You would say, okay, well, this is a nice rule for like the integral of cosine dx is sine of x, but I don't really want to memorize that the antiderivative of negative sine of x is cosine x. I'd rather memorize that the integral of sine of x dx is negative cosine x, right? So if you take 3 seconds to type into Google rules for antiderivatives or rules for integration, you will find a very pretty sheet full of these rules that you can proceed to memorize if you so choose. Okay? Right. So here's the one that's a catch, is you have to have absolute values here. Okay? And then, right, so this looks a little bit sticky because, right, it's the same idea as you're not going to memorize the rule for negative sine x, you're going to memorize the rule for sine x. Chances are you're not going to memorize a rule for n x to the n minus 1. You'd much rather memorize a rule for x to the n. Challenge for Friday. Tell me what that rule is. I'm not going to tell you right now. I want you to think about it. Don't Google it. Think about it. Okay. I want you to, heck, by the end of class, if you tell me what it is, I'll give you a bonus on something. I'll think about what it is. Okay? With an explanation. So the question is, what is a rule for this? You have to tell me at the end of class. Okay. Question.
So, a little bit on the homework last night, there were some antiderivatives that didn't look complete, or not antiderivatives, integrals that didn't look like they had been completely differentiated, so it confused me. Does that make sense? So, like, for e to the x plus 7,
Like this?
Like x plus 7 is in the
Oh.
exponent.
Like that?
Yeah. I don't understand how that can be the derivative and where the or it was like 2x plus 7, like where the 2 went, you know? Does that make sense? I'm trying to
2x plus 7?
Yeah, if it's 2x plus 7, like where that 2 went in the differentiation, like from the whatever the antiderivative is. Does that make sense?
So, yes. So you're thinking that, hey, it seems like this might be the antiderivative, right?
Yeah, but then you still have to multiply that by 2.
So if I take the derivative of e to the 2x plus 7, I have to multiply by 2. But I don't have a 2 here.
So would it be?
So I account for that.
Okay.
Okay. So in terms of the, here's a nice opportunity to see the u substitution in action, right? So I need more clean space, though. Let me get more clean space. Nope, not there. Clean space. Okay, so let's say that we are still trying to find this integral, right? I'm going to look for the complicated looking thing. That's complicated looking, and it's the inner function of composition. So what's the derivative of u? 2. That means that little changes in u are gotten by 2 times little changes in x, right? But notice that my original integral didn't have a 2. So it only had a dx. So let me do this. I solve for dx so that I can now rewrite this integral as e to the u times 1/2 du. And bring the 1/2 out, because remember, we talked about the constant multiple rule. And then an antiderivative of e to the u is e to the u. But then u was 2x plus 7. Okay, so this is u substitution in action, right? This is what it's meant for. Okay, chances are most of you did what I did originally, which is said, oh, it looks like it should probably be e to the 2x plus 7, but then you realize you get an extra 2 if you take the derivative, so you just divide out by 2 to account for it, right? So this is eyeball, right, down here, and this is U substitution up here. Question? Here. So I rewrote e to the 2x plus 7 as e to the u. And then the 1/2 du right here, right, came from saying that dx is equal to 1/2 du. So then I can pull out a constant multiple. So I pulled out the 1/2 and then took the integral of e to the u, du. Okay. All right. Can I change the slide? How are we doing? Good? Okay. So then I'm just going to say it because I'm going to have to click through the whole thing if I redo it. So sometimes substitution method helps you see structure that is otherwise hard to see. And that's the moral of the story here. Okay. Oh, I guess there was a good example on here. So here's another example of a function that would be so tempting to be like, ooh, it's a quotient, right? I just take the antiderivative of the numerator and the antiderivative of the denominator and I leave it as a fraction. So tempting. But that's not the way it works, right? So what you could do instead is to say, all right, well, I've got a cosine and a sine. I know that those are related by derivatives. So let me just think, well, if I had sine of x in the bottom, right, so I could think 1 over sine of x. That's a composition of sine of x and the 1 over x function, right? And the derivative of sine x is cosine x. So I sort of have all the right pieces to say that I've composed 1 over x and sine of x. And if I think about the derivative of 1 over sine x, I will in fact get this, right? Now, that's hard to imagine all in your brain. So another way to do it would just be to write it down and say, okay, well, I've got sine x in the denominator. Its derivative is cosine x. So that means little changes in u correspond to cosine x times little changes in x, which will allow me to rewrite this integral as 1 over u du. So you see it, we've taken our cosine x over sine x dx. We sort of separated it out to look at this chunk. And then this thing using u becomes 1 over u, and then this thing is du. This integral, nice and pretty, right? I know how to take the antiderivative of 1 over u. It's natural log of absolute value of u, right? Plus c. And so then I can just plug back in my sine x for u, and we're done, okay? But again, so what would have happened if you had instead looked at this and been like, well, I'm going to let u equal cosine of x, right? Because that would have been a legitimate choice too, okay? And so I just want to show, because I feel like too often we only talk about the right way and what happens if you start down a path that gets ugly. Okay, so let's look at that. So let's pretend that we didn't think about using sine of x first. So we're going to use cosine of x first. Okay, so then the rate of change of u is going to be negative sine of x. I've already introduced a negative. That makes me a little uncomfortable, but not too bad, okay? Because sometimes that happens. You introduce extra constants that you didn't really want, but you can take care of constants. Constants aren't evil, okay? So this means that little changes in u correspond to negative sine of x times little changes in x. This is sine of x times dx. And in my original, I don't have sine of x times dx. I have 1 over sine of x times dx. As soon as I see this, I'm thinking I picked the wrong u. Because there's no easy way to rewrite the original integral in terms of this u, right? I'd have to somehow like, I'd have like the integral of u, and then if I put a du here, then I'd have like a negative to account for that negative, because there's no negative here. And then I would need sine x in the denominator, but right now I have a sine x in the numerator. So I'd have to have like sine squared x in the denominator, and that's not in terms of u. So then I'd have to figure out how to rewrite this sine squared x in terms of u. Shoot, that would be like negative u over 1 minus u squared. That's gross. We did not make this prettier, right? We made this way uglier. So that is our cue that we picked a bad u. Very bad, okay? The process of u substitution is meant to make your life easier, not harder. So if you find yourself having to do crazy, crazy stuff, go back, pick a different u, and try again, okay? How are we doing? Okay. Always try to eyeball first, unless you really, really just like u substitution. I found it relaxing when I was an undergrad. I'm also a little bit weird. If unsuccessful, let u equal something and differentiate, okay? And then make adjustments as necessary. So if you find yourself going down an ugly path, don't persist, okay? Go back and try a different route, okay? Okay, I feel like I've drilled this in enough, but just to make sure, can you guys attempt this one really fast? So I want you to evaluate this definite integral from 3 to 7 of cosine x sine x dx. Take a minute. You can talk to a neighbor if you want to. What'd you get? You didn't get, so talk. Do you have an idea, Taylor? No? So the antiderivative of cosine x sine x should just be negative sine x cosine x, right? Because I take the antiderivative of cosine x and the antiderivative of sine x and I just multiply them together, right? No. Right? This is super bad. Super bad. Don't do that, okay? What do we think of instead? The chain rule, right? I've got a product of functions, and one is the derivative of the other. Yeah? So, give it to me. What do I say? So the derivative of sine x is cosine x, right? So this would mean that if I let u equal sine of x, then the derivative of u would be cosine x. So that means little changes in u correspond to cosine x times little changes in x. Check it out. That means I could rewrite this without the 3 and the 7 as u du. Why didn't I write 3 and 7 here? Yeah? Right. So notice I made a point of writing x equals 3 and x equals 7. Because if I switch to u's, the bounds are no longer 3 and 7. I have now changed sort of the input, if you will, of what I'm looking at, right? So if I wanted to include bounds, I would have to actually substitute in 3 for x and 7 for x and write the bounds on u. So it would be like sine of 3 to sine of 7 if I wanted to keep track of my bounds while doing the u substitution. Okay? Now, if you don't want to keep track of your bounds, you don't have to. Just make sure that at the end you rewrite everything in terms of x. So let's see what that looks like. So what's an antiderivative of u? Oh, no, an antiderivative of u. Antiderivative, right? U squared over 2 plus c. Okay, but I started out in terms of x. So that means that this thing should be u was sine of x. So sine of x squared over 2 plus c. And then evaluated from x equals 3 to x equals 7. What's the derivative of u squared over 2? U.
So it could be
Ooh, I'm sensing a pattern.
oh no, because
So, yeah, remember my question. What is this thing? Okay. We're getting close to an answer. Okay. So final answer here would look like sine of 7 squared over 2 minus sine of 3 squared over 2. Right? Because remember, this notation means evaluate. Why didn't I write plus c? Adam? Oh, Maxwell? Because the c's will cancel. What does that mean? So if I had, if I evaluated this at 7, I'd have a plus c, and then minus this thing plus c, but then c minus c, they cancel, right? Okay, so don't worry about those. Okay, all right. Aw, sad. Okay, so we are getting so close, but as much as I always try to cram as much as I possibly can into one day, we are actually not behind. So on Friday, we're going to talk about an incredibly superficial interpretation of the integral, okay? So I saved it for last because I don't really want it to be the only thing that you guys think of when you think of an integral. Yeah, so you've got homework on my math lab, and we will, just FYI, just so you have the big picture, right? We will have one more quiz this semester, next week in recitation, but starting next week, we will be studying for the final, okay? Which means you should start studying for the final so that we can make next week as productive as possible with your questions, okay? So start studying. Ooh, and fill out my teaching evaluations, please, please, please.
Are you giving office hours?